So, welcome again to the new lecture of this course, Fundamentals and Applications of Dielectric Ceramics. So, let us just recap what we did in the last class. So, in the last class we looked at detail little bit further into impedance spectroscopy, and this is a very useful tool to determine the dielectric characteristics of the materials. So, many materials show non-ideal behavior, and as a result their description is incomplete by a device circuit. So, as a result you would like to invoke other electrical circuits to model them, and for this it is useful to measure properties such as complex impedance. Complex impedance contains real and imaginary part, which are basically calculated by measuring Z and theta. So, theta will also allow you to measure that loss tangent, and from this modulus electrical impedance you can determine modulus, and by combining temperature dependent, temperature and time dependent measurements. Time means frequency, right? Dependent measurements, one can determine things like Ri, Ci. I means certain entity. So, resistances and capacitances, you can also calculate what are the time constants, and from these temperature dependence of these one can also determine what is the activation energy, and then one can look into mechanisms of electrical dielectric materials, mechanisms of conduction, etc. So, you might have vacancies, you might have interstitials, you might have impurity atoms, so on and so forth. So, different things will have different entities will have different time constants, and they will have different temperature dependence and frequency dependence. As a result you can look into different mechanisms a little bit more clearly, and by combining this impedance and modulus spectroscopy the differences become more amplified, or you can say clear. So, this is one way to characterize dielectric materials, and a very useful way. And then we looked at dielectric breakdown, and dielectric breakdown is basically when the dielectric materials become conducting or they stop functioning as a dielectric, and this is this could be because of increase in electron temperature or sudden conductivity, or because of thermal buildup. Temperature buildup again makes materials conducting, and it could also be because of defects in the material such as porosity, grain boundaries, etc. So, there are multiple mechanisms that we briefly discussed. We did not get into details of this, but if you want to get into details of dielectric breakdown, I suggested to read this book, Principles of Electronic Ceramics, by Hench and West. So, this is a very nice book which gives you a good insight into dielectric breakdown. So, now what we are going to continue about in this lecture is we will look at we will now continue our discussion into what we call as nonlinear dielectrics. Okay. And nonlinear dielectrics we mean by this, what we mean is that when you apply electric field, let us say polarization. So, we saw in case of linear dielectric that P is equal to epsilon naught into epsilon r minus 1 into E. This is what is the, so basically this polarization increases as a function of electric field linearly. So, when the field is 0, the polarization is 0. So, as a result you have a linear variation of polarization. This is what is a linear dielectric. Okay. But in case of non-linear dielectrics, especially at higher fields, you might have different effects. So, for example, a ferroelectric material will show a hysteresis loop, a polarization switching loop like this. It has certain linear part at low fields, but that linear part is limited, but rest of the places the curve is pretty non-linear. So, this is a non-linear dielectric. So, these non-linear dielectrics have special characteristics, and generally we classify them in three categories. One is called as piezoelectric, second is called as pyroelectric, and third is called as ferroelectric. And these have crystallographic basis of distinction as well as thermodynamic basis. to understand these. So, what we will do is that to begin with, so far what we did earlier, we looked at the properties of a dielectric mostly in scalar form, but to understand ferroelectrics, piezoelectrics and pyroelectrics, it is important to invoke the tensor form of these properties. So, what we will do is that first we will introduce the formal notations for these properties in the tensor form. Okay. So, what we will do first is that we will look at the properties relevant to these materials in tensor form. So, I assume that you have some knowledge of tensors and matrices, okay, and you would also have some knowledge of thermodynamics. If you do not have knowledge of these subjects, then I would say you look at the other MOOC courses or other books. Okay. So, for example, for looking at tensor properties of crystals, I can recommend by Nye. This is a very nice book on tensor properties of crystals, and let me give you one or two more references. So, this is basically, you can say, physical properties of crystals. Physical properties of crystals by Nye, J.F. Nye basically. So, this is first book, and then to learn about thermodynamics you can read, let me give you, so second one could be modern course in statistical physics, which is by L.E. Reichel, and third I can recommend is Principles and Applications of Ferroelectrics and Related Materials. This is by M.E. Lyons and A.M. Glass. This is a classic book on ferroelectricity, which goes a bit into phase transitions and thermodynamics and things like that. This is more about statistical mechanics, thermodynamics. This is more about tensor properties or physical properties of crystals. So, these are some books, otherwise there are a lot of other books, you can also look at them. So, let us begin with some discussion on this. So, our discussion will remain on, basically we will use system will be, coordinate system will be Cartesian, and we will use x, y, z coordinates, and then z will be considered as perpendicular to the plane of the film or plane of the substrate or plane of the paper. Okay. So, let us first begin with the tensor definition of properties. Okay. So, first let us begin with the dielectric permittivity. So, among dielectric properties, the first thing that we know is the polarization, right, which we saw is P, but in this case we determine as Pi. So, that determines, the I determines the direction, right, and the units are Coulomb per meter square. So, when you apply a electric field vector, let us say electric field is also EI, it could be EI, EJ, EZ, whatever. So, again this is in volt per meter. So, when you apply electric field to a dielectric crystal, you generate a polarization, and this polarization is written at Pi is equal to chi ij Ej. Okay. So, this is your basically applied electric field vector Ej, and this is the polarization Pi. and so you apply the field in j direction and you measure the field in I direction, polarization I direction, and this chi ij is known as susceptibility tensor. So, just like we have magnetic susceptibility, here we have dielectric susceptibility. So, this is dielectric susceptibility tensor, this is in farad per meter, and as you can see this is a second rank tensor. So, basically chi ij you can write as chi 11, chi 12, chi 13, chi 21, chi 22, chi 23, chi 31, chi 32 and chi 33. So, this relation however is valid only for linear dielectrics or the linear portion of the nonlinear dielectric. So, when you make polarization versus electric field diagram for a nonlinear dielectric, you can apply this relation only to the linear region of that plot, not to the other plot. So, now let us see what is the total surface charge density. So, total surface charge density which is essentially dielectric displacement when you apply electric field. So, we can write this as dI to be equal to epsilon naught EI plus PI. So, here this is permittivity of free space, which is 8.85 into 10 to the minus 12 farad per meter, and EI is the basically you can say the field, and PI is the polarization that is generated. So, now if you combine so if you let us say if you write this as equation number 1 and if you write this as equation number 2, I can write this DI as DI can be written as epsilon naught EI plus chi ij Ej, okay, and this can be written as epsilon naught delta Ij Ej plus chi Ij Ej, which can be written as epsilon naught delta Ij plus chi Ij into Ej, where delta Ij is called as Kronecker delta, which is equal to 1 if I is equal to j and 0 if I is not equal to j, okay. And this particular thing is called as basically you can write this as epsilon Ij Ej. So, epsilon Ij is equal to epsilon naught delta Ij plus chi Ij, and this is basically the dielectric permittivity that we say dielectric which we were earlier writing in case of in the form of scalar form, okay. And this epsilon Ij is basically you can say it is a product of epsilon naught into something, right. So, it is epsilon naught delta Ij plus chi Ij, and this for a ferroelectric kind of material, for the materials for which the susceptibility is really large, for them, for materials with you can say large susceptibility, you can say this is equal to chi Ij, because the free space component is very small. And we can also write this epsilon Ij as epsilon R Ij into epsilon naught or kappa Ij into epsilon naught, where this is called as dielectric constant. So, when you say high K dielectric or low K dielectric, this is the kappa, and which is also nothing but epsilon R, okay. So, this is what is the more useful term epsilon R or kappa than epsilon Ij, okay. So, you can see that here also that epsilon Ij is a rank 2 tensor. So, which means it has 9 components. Often we will see in many of these dielectric properties or other properties as well of second rank tensor, third rank tensor, fourth rank tensor, is that they, although let me just briefly introduce what tensor is. So, we know that tensor is defined by a rank by the formula 3 to the power n. So, when n is equal to 0, it has one component. So, this will become a scalar. When n is equal to 1, it will have 3 components. So, this will become a vector. When n is equal to 1, it will have 9 components, n is equal to 2, sorry, then it will be second rank tensor. So, vector is a rank 1 tensor. Okay. So, this will have 9 components. So, this is a tensor of rank 2. When you go to n is equal to 3, you will have 27 components, and then it will be a tensor of rank 3, and generally we see up to 10 to the power n is equal to 4, which is 81 components, and this will be tensor of rank 4. So, this is how these will be. So, when you see something like epsilon ij, it is basically tensor of rank 2. Okay. So, this is what it will be. So, when you write, for example, as we will see in case of stiffness, if you write f s I j k l, then this is tensor of rank 4. It will have 81 components, but we are fortunate that crystal symmetry and thermodynamic arguments reduce the number of components, but this is how it is, this notation means. So, this is as we say is the dielectric, and in case of dielectric permittivity, we say that epsilon I j is this. So, epsilon I j is a rank tensor of rank 2. So, it will have 9 components, but basically using the free energy arguments, this reduces to 6 independent components. So, that we will see later on. Okay. So, you can have thermodynamic consideration, you can have crystal consideration, and so on and so forth. So, 9 is reduced to 6 using thermodynamic considerations, and 6 can be reduced to even further if you have. So, for example, if you take for a cubic crystal, it will have lesser components. If you go for a monoclinic or a tetragonal crystal, it will have more. So, more asymmetric the crystal is, more the components you will have. More symmetric the crystal is, lesser the number of components will be. So, that is a general guideline. So, these 9 components can be reduced to further lower number depending upon the crystal symmetry and thermodynamics. So, now let us look at the second aspect, that is elastic properties. So, in the elastic properties, let us first define the stress. So, this is stress which is in Newton per meter square. So, this is capital X I j. So, this is the stress that is applied, and then you measure the strain, which is small x I j, which is strain which is unitless. So, if you apply stress on a elastic material within the linear region, within elastic limit, you apply Hooke's law, right? And what does this Hooke's law say? This says x I j is equal to small s I j k l into capital X k l. Okay. So, this is the stress, this is elastic compliance whose unit is, no, it is inverse of Newton meter square, so meter square, and this is strain. So, you can see here that stress is a rank 2 tensor and strain is again a rank 2 tensor. The elastic compliance as a result is rank 4 tensor. So, this is a proportionality constant, basically it turns out to be rank 4 tensor. So, basically you can say it is a and stress is rank 2, strain is rank 2, and so you can write stress as x11, x12, x13, x21, x22, x23, x31, x32, x33. So, it has 9 components, but by symmetry it will reduce to 6. Similarly, strain will also reduce to 6 because these two are equivalent, this and that is equivalent and these two are equivalent. So, as a result you will reduce them to 6 components because of crystal symmetry. So, this is the relationship between strain and stress using elastic compliance as a proportionality factor. So, this is equation number, let us say. So, we may have to use numbering system. So, this is 1, this is 2, this is 3 and is that 4? Yeah, this is 4 and let us come to equation number. So, and the inverse form of the above equation is, so inverse relation would be x I j is equal to C I j k L into x k L. So, this is strain, this is elastic stiffness or elastic modulus, this is again a rank 4 tensor, this is in Newton per meter square and this is stress. Okay. So, now that you have elastic, you have, so this is let us say 4 A. Okay. So, we know that these two equations are related to each other. So, as a result we can relate the stiffness and the compliance using the relation. So, we can relate them as small s I j k L into small c k L m n, this is equal to C I j k L into small s k L m n, and this is equal to delta I m into delta j n. So, obviously delta I m is equal to 1 when I is equal to m, and so basically delta I m is equal to 1 when I is equal to m and is equal to 0 when I is not equal to m. Similarly, delta j n is equal to 1 when j is equal to n is equal to 0 when j is not equal to n, and this you can write the matrices and prove it. It's not difficult to prove it. So this is the relationship between the elastic compliance and the stiffness, and let us say this is equation number 4b. Okay. So, these stress and strain tensors are stress is I j, these are all as we said second rank tensor, but they are symmetric in nature. Okay. And what it means is that basically chi I j is equal to chi x I j is equal to x j I and small x I j is equal to small x j I. So, as a result the total number reduces to 6. So, basically 6 components, and when this happens as a result since you have a strain, there is a symmetry in stress strain, this also reduces the number of components in stiffness. So, for example, compliance becomes S I j k L to S j I L k. So, number of similarly you can write for C slash S. So, for both stiffness and compliance the number of components. So, in a 4th rank tensor you will have 81. So, this 81 reduces to 36. So, you can write the matrix and then you can use the symmetry arguments and see which ones are similar. Because we are saying I j is equal to j I and I j is equal to j I for a strain also, what it also means is that this k L will be equal to L k. So, when you make these combinations you will see that 81 components will reduce to 36 and crystal symmetry further reduces these components to 21. So, when you apply crystal symmetry, because crystals are symmetric, so the crystal symmetry arguments further reduces these to lower numbers such as 21 or so, and so when you apply crystal symmetry plus thermodynamics, actually I should say both of them. So, both of these arguments reduce to 21 or lower. So, we are fortunate that from 81 we get down to 21 or even lower components, and for symmetric crystals which we generally deal with have even lower number of components. So, it makes life easier. So, this is tensor notation for elastic properties. Now, we do not look into plastic properties because dielectric materials are ceramic materials, as a result they do not have plastic deformation. So, we mostly deal with the elastic properties in these materials. So, next we will look at what we call as, we probably are going to run out of time, but next is what we call as piezoelectric properties. So, let us first define piezoelectric materials. Piezoelectric materials are those which are first of all non-centrosymmetric. Okay. Among crystal classes, there are certain classes which are centrosymmetric, there are certain classes which are non-centrosymmetric. Non-centrosymmetric means they do not have lacking a center of symmetry. So, for example, what does it mean? It means that let us say you have 2 points x, y, z and another point minus x, minus y and minus z. If you have a center of symmetry, so if you have a center of symmetry, then what you see, so if you do an inversion operation, then x, y, z can be replicated to minus x, minus y, minus z if you have a center of symmetry, but if you do not have center of symmetry, then x, y, z will not be equivalent to minus x, minus y, minus z. There is a very basic definition of piezoelectric materials. So, piezoelectric materials by definition have to be non-centrosymmetric, that is a must requirement. Okay. So, we are probably going to run out of time now. So, we will just briefly summarize this, that we have discussed about some tensor properties of materials, mainly right now looked at dielectric properties and elastic properties, and we will further discuss the piezoelectric properties and other properties of these nonlinear dielectric materials in the next few lectures. Thank you.